All right, everyone, welcome back to Calculus 3. So today we're going to continue learning how to do triple integrals here. So last time we saw triple integrals in rectangular coordinates, but just like double integrals, we can often transform our coordinate system and make things a lot easier for ourselves, especially when there's circular symmetry or spheres or cylinders or things like that involved. Now, today, what we're going to do is we're going to practice transforming triple integrals into cylindrical coordinates. And then in lecture 26, our last one of this unit, we're going to practice doing triple integrals in spherical coordinates, which will be kind of similar, but maybe a bit different from doing cylindrical coordinates here. All right, so let's go ahead and talk about this. So if we're going to change into a different coordinate system, well, then you might ask, okay, well, is there some kind of Jacobian for triple integrals? And the answer is yes, there is. So if you have X, Y, and Z, so you start off with one coordinate system, and you want to change to a different coordinate system, maybe with variables U, V, and W, you first get your original coordinates as a function of the new coordinates here, and then you need to compute the Jacobian of the transformation. And this time the Jacobian is the determinant of a 3x3 matrix. And this makes sense because we just take each variable and we differentiate them with respect to each one of the new variables that we have here. So we have partial x, partial u, partial x, partial v, and partial x, partial w. And then we do the same for y, and then the same for z. And then whatever this ends up being, we slap an absolute value sign on it here, and we put it into our integral. So the original triple integral can be written like this. And don't worry, these triple integrals aren't this long. The only reason why this is very long is because each one of our original variables now depends on 3 variables. So they have to list 9 different things here. But now we have x in terms of the new variables, y in terms of the new variables, z in terms of the new variables. And then we stick the absolute value of the Jacobian there, just like before here. All right, and dv is equal to all of this right here. So anytime you see a dv and you want to switch it into a different coordinate system, you need to include the Jacobian as well. All right, now, unlike when we learned about Jacobians with double integrals, we're not really going to do much with just kind of a general transformation. Like, we're not really going to give you random U's and W's to switch into. But there will be specific things that we need to do with this. And 2 of them are flipping into cylindrical coordinates and flipping into spherical coordinates. So what we're going to do here is we're going to compute the Jacobian once for each of those, and then we really won't have to worry about it. We just have to remember to put it into our integral. So let's go ahead and do this for cylindrical coordinates here. Okay, so cylindrical coordinates are useful when you want to have some kind of circular symmetry with 2 of your coordinates, but you still want to keep one of them being rectangular. So maybe you have 2 surfaces with defined as z equals something, but then you have some kind of circular symmetry in x and y. That would be an excellent time to use cylindrical coordinates. And just a personal opinion, cylindrical coordinates is kind of my go-to coordinate transformation. So that anytime there's any kind of circular symmetry, I usually am going to change into cylindrical coordinates by default, not spherical. The only time I would do spherical by default is if there's a literal sphere in the problem. But the rest of the time, I'm probably going to change into cylindrical coordinates as my first guess here. So that's kind of how I think about this. Anyways, let's go ahead and compute the Jacobian for cylindrical coordinates so we can stick that into our integral. All right, so let's write down the conversion formulas for cylindrical. We have x is r cosine of theta, y is r sine of theta, and the kind of stupid transformation z equals z. So we're not really doing anything with z here. That's staying the same. So what's going to happen here? So let's compute our Jacobian. So this will be partial x, partial r, and then theta, and then z. We have the same thing with y. And then we have the same thing with z. Oops, that's an r. Gosh, keep doing the rectangular coordinates. This should be a theta. Then we have partial z, which is a little bit silly. All right, so let's go ahead and do these derivatives. So the derivative of x with respect to r, well, it's just a constant times r, so it's going to be cosine of theta. Partial x with respect to theta will be negative r sine of theta. And partial x with respect to z, well, there aren't any z's in here at all, so that's just going to be 0. Next, we do y with respect to r here, and get sine of theta. Then we do the derivative of y with respect to theta, and have r cosine of theta. But then the derivative of y with respect to z is again 0, because there aren't any z's in here. Now, z is really easy. There aren't any r's in this. There aren't any thetas in this. And there's a z in there. And the derivative of z with respect to z is 1. So this is what we're going to get with our Jacobian here. Nicholas has a guess. It's just going to be r again. We'll see if that's correct. So we needed to do the determinant of a 3x3 matrix. So the way we do that is we do it by minors. So we do cosine of theta, and then we have this minor. Then we subtract negative r sine of theta. So that's really just adding r sine of theta. And then we have this minor. And then we have, well, 0 times this minor, but actually both this and that minor would all be 0. So I'm just not going to write that part. All right, so if I do this determinant, I have r cosine of theta times 1, and then I subtract 0. So I have r cosine squared of theta. And then here I do the same thing, only this time I have just a sine of theta times 1 times r sine of theta. All right, and Nicholas ended up getting it right, because if we factor out the r here, then we just have r as our Jacobian. And we don't even need to put an absolute value on it, because remember, when we're doing integrals in this class with polar coordinates, we're assuming that our r is positive. So the Jacobian, anytime we want to use cylindrical coordinates, we're just going to put r there. This means that our differential dv is going to be r dz dr d theta. So it's effectively just polar coordinates, and then we just throw an extra dz in there. Unfortunately, spherical won't be so easy, but we'll worry about that another day, i.e. Monday. All right. So triple integrals with spherical coordinates. Now that we know the Jacobian, we can do these. So let's see. So if f is continuous over this solid region, where we have cylindrical coordinates here, and z is between these two surfaces, u1 of r theta and then u2 of r theta, and r and theta are in this two-dimensional domain D, then what we could do here is we could write the triple integral right here as the double integral over D, and then the integral from u1 r of theta to u2 r of theta of r dz dr d theta. So effectively, we do this integral with respect to z first, and then once we're finished with that, then we just go back to doing a polar double integral, which we already have experience doing here. Now, in particular, if we're able to bound our r in between two functions of theta, then we could further write this out as the integral of, oh, oops, I forgot the function here. Let's put the function in there, we need that. R dz dr d theta. And then we have u1 of r and theta and u2 of r of theta, so those are surfaces. Then we have our one-dimensional curves, which is g1 of theta, g2 of theta. And then we have our angles, where it seems our angles go from alpha to beta right here. And there we go. So that'd be how we would set up that triple integral in cylindrical coordinates. And oh, I guess I said this on the previous page, but dv, the differential here, is going to be r dz dr d theta. So we can't forget to put that extra r in whenever we flip into cylindrical coordinates. So basically, to summarize everything I've just said, cylindrical coordinates are where we turn x and y into polar and we leave z alone. That's what cylindrical coordinates are. All right, so let's go ahead and get some practice with this. The rest of the class will just be actual practice using cylindrical coordinates here. So we have to differentiate z first. Well, we integrate with respect to z first, and then we just have dr and d theta here. What's the lower bound of the second integral from the last one? Oh, it's u1 of r and theta. And then we have g1 of theta to g2 of theta right here. Is our theta plane just the xy plane? Yeah, that's right. Our theta plane is the xy plane. Because you could write any xy coordinate you have in terms of r and theta. Is it easier to integrate z first? Typically, when you use cylindrical coordinates, yeah, it is. All right, let's get a demonstration of this. So I want to do this triple integral, the integral from -3 to 3, 0 to √9 minus x squared, and then 0 to 2 of 1 over 1 plus x squared plus y squared dz dy dx. All righty. So let's first figure out what kind of domain we have here that we're integrating over, and then we'll convert everything into cylindrical coordinates. All right, so let's see here. So the nice thing here is that, remember, so the first integral we do is between two two-dimensional surfaces. The next integral is bounded between two one-dimensional curves. And then the final integral is between two zero-dimensional points or numbers. So we kind of descend through all of the dimensions here. So if we have z equals 0 and z equals 2 as our first bounds right here, what type of surfaces am I going to be in between? What names should these surfaces have? What are they called? They're planes. That's right. So we're going to be in between the flat plane, z equals 2, and then the flat plane, z equals 0. So we're going to be from here to here, and we're kind of cut off by flat planes. Now I'm going to hold off on drawing those until I know what my domain in the xy world looks like. All right, now once I deal with that, then I'm on the xy plane dealing with y, and y goes from the line y equals 0 to y equals √9 minus x squared. So √9 minus x squared is this half circle like this of radius 3. And then y equals 0 will be this line here. So if we draw this on our 3D picture here, we have this half circle. And then have a half circle up here. And then we have this. So it's effectively like a cylinder that's cut directly in half. That's what this looks like. And x goes from -3 to 3. So we have all of this half circle right here. All right, so now that we know what we're integrating over the half of this cylinder right here. Let's convert everything into cylindrical coordinates. So let's see here. So we have those. Now, the nice thing about cylindrical coordinates is we can keep z exactly the same. So I don't need to worry about changing these bounds here because I'm still going to use z in this. So I have dz, and that goes from 0 to 2. So that's a nice thing about cylindrical. Let's change the integrand here. So what will the new integrand be, including the Jacobian? What will it be? Oh, you're really close. So you gave me the bounds here, which is really good. That's right. So this is 0 to pi. This is 0 to 3 right here. But all I really wanted was the integrand, which is going to be r, which we get from the Jacobian. And then this will turn into 1 over 1 plus r squared. All right, so then we already have these questions answered. Thank you. This will be dr and d theta right here. So r goes from 0 to 3 right here, because it's a circle starting from the origin at 0, going all the way out to a circle of radius 3 here. And our angle goes from 0 to pi, because we go halfway around this circle right here. So this is what we're doing in cylindrical coordinates here. And this is going to be an easier integral to do. Now for this one, since I have constant bounds for all of my integrals, I could split this up into multiplication of 3 different things. So I could rewrite this integral as the integral from 0 to pi d theta, the integral from 0 to 3 of r over 1 plus r squared dr, and then the integral from 0 to 2 dz right here. So there's our nice multiplication trick at work here. All right, so the integral of d theta from 0 to pi is just pi. We'll handle this one in a minute. And then the integral from 0 to 2 of 1 dz is 2. So I'll just stick the 2 right over here. So we have 2 pi times the integral from 0 to 3 of r over 1 plus r squared dr. Now I think someone already said this in the chat at least. How do we do this integral, r over 1 plus r squared? We're going to use u sub. Ooh, I guess we could use trig sub if we wanted to, but I definitely prefer u sub here. Trig sub is definitely a last resort for me personally. So du will be 2r dr. So 1/2 du will be r dr. All right. So we have the 2 pi times the integral. Now I'm going to change my bounds here to save time. So I'm going to plug 1 in here for 0 in here for r, and I get 1. Then I'm going to plug 3 in here for r and get 10. And then I have 1/2 1 over u du right here. All right. So the 1/2 and the 2 will cancel. The integral of 1 over u will be natural log of absolute value of u. This is from 1 to 10. So we have pi ln of 10 minus pi ln of 1, but we all know that ln of 1 is going to be 0. So this is ln of 10 times pi. That's going to be our answer for this triple coordinate or triple integral here. All right. There's one example. Let's do a few more. Next, evaluate the integral in cylindrical coordinates. Okay, that's what we did for the last one. Now, once again, we got lucky here. It seems like the surfaces that were in between are z equals 0 and z equals 2. So these are just going to be planes. So let me draw that again. Okay. This time our xy drawing will be a bit different. So we have x is √3y as the lower bound for x. So x is √3y is kind of something like this, like a diagonal line like that. So this is x is √3y. And then the other one is x is √1 minus y squared. So x equals √1 minus y squared is going to look like this right here. Okay, now since this was the upper bound for our x, then that means that we're doing potentially all of this right here. Now, how much of this we're doing depends on the next part. So y seems to only go from 0 to 1/2. So we're not doing this bottom part with y being negative. We're starting at y equals 0. And 1/2, actually, that's going to be right here where these guys intersect. Because if we plug in y equals 1/2 in, I have x is the square root of 1 minus 1/4, which is the square root of 3/4, which is √3 over 2. But then if I plug in 1/2 for this, I also get √3 over 2. So y equals 1/2 will be at the same place for both of those right here. All right. And so that means that we're looking at this little piece of pie right here. This is going to be our region in the XY plane, or the r theta plane as we're calling it now. Okay, so what does that mean our picture looks like? Well, we start drawing a little arc of the circle here. This will be our domain. And then we go up here, have a copy of it there. So it kind of looks like a wedge or a slice of cheese or something like that. We're trying to integrate over that domain here. All right. So now that we know that, let's go ahead and convert everything into cylindrical coordinates. I keep almost saying polar coordinates, but that's essentially what we're doing here. We're turning the x and y into polar coordinates. All right, well, z remains the same. X squared plus y squared in polar is r squared. And then for our integrand, we have to remember to include the Jacobian, which is r. And we have dz, dr, d theta right here. All right. So now let's go ahead and figure out what our r bounds will be. So we include the origin here. So r equals 0 will probably be our lower bound here. And then our upper bound is where we hit this circle. Remember, this is a circle of radius 1 centered at the origin, AKA the unit circle. So this will go from 0 to 1 with r right here. And then finally, we're going to rotate through a certain angle, but it's not going to be a very wide angle. We start at theta equals 0 for sure. And then what angle are we going to stop at? What angle has the coordinates √3/2, 1/2 on the unit circle? Very good, pi/6. Yeah, that's the rigorous way of doing it, Robert. Narrow angle is probably pi/6. Honestly, that's what I thought when I looked at this problem. Yeah, so we have pi/6 right here. All right, so then let's go ahead and do this one. And once again, we have all constant bounds, so we can go ahead and split this up into 3 pieces. So we have 0 pi/6 d theta. We have 0 to 1, and I guess this is r squared dr. And then we have 0 to 2 dz right here. All right. So let's see here. The integral from 0 to pi/6 of d theta is pi/6. The integral from 0 to 2 of dz is 2. So I'll just stick that here. And then we have to do this as well. All right. So let's go ahead and integrate here. This is going to be a pi/3 now if we combine those. And then I have 1/3 r cubed from 0 to 1. Now, if I substitute in these bounds here, I think we've seen this quite a bit before with polynomials with bounds like this. We put 1 into here, and then I plug in 1 here, and we end up getting pi/9. So that's what we're going to get from this integral right here. So once again, we took something that looked a little bit kind of scary in rectangular coordinates, and we were able to turn it into something very simple in cylindrical coordinates. And anytime you have some kind of circular domain, it's worth considering changing your integral into cylindrical coordinates. All right. Next one here. Describe the solid region whose volume is this. So this is technically the integral of 1, so it represents a volume right here. And then what we're going to do is we're going to describe what this region is, and we're going to find its volume in 2 different ways, actually. So let's go ahead and take a look at this. First, we're doing z, right? Our upper bound for z is the constant 3, so that's going to be a plane of height 3. Now this time we don't have a plane as our lower bound. What kind of shape is this going to be for our lower bound? Does anyone know what this is? It's a cone, that's right. So this is a cone. So it's going to go up like this. So what happens is we have this cone. Oops, I guess it doesn't go all the way around. If we look at our y coordinates here, we go from y is 0 to the square root of 9 minus x squared. So it's going to be another circle of radius 3 here. And x does go all the way across, so we will go from -3 to 3. So I guess what this is going to be is this is going to be a cone. We're going to get rid of that part. This is going to be a cone that's going to be cut in half right here. So this is a cut in half cone. That's what we're trying to find the volume of. All right. So what's going to happen now is I'm going to turn this into a cylindrical coordinate problem. So my integrand is very easy to deal with because I just have 1 in there. So that means all I'm going to have is an r when I put the necessary r in for the Jacobian. All right, next, remember z can remain the same, although this will need to rewrite differently. How should I write this in terms of cylindrical coordinates? That's right, you guys got it. It's going to be r. This x squared plus y squared is r squared. If we do a square root of that and get r. All right, and then r itself will range from 0 to 3 because we're going from the origin out to a circle centered at the origin of radius 3. And then theta, well, we're going halfway around the circle here, so it seems that theta will go from 0 to pi. This blasted r right here is preventing us from using the multiplication trick again, so I guess we'll just have to do this the old-fashioned way of doing one integral after another. So let's see here. The integral of this with respect to z is going to be r times z from r to 3. All right, and if I substitute that in, all right, let's see. If we put this in here, we're going to have 3r minus r squared. Okay, actually, now that our integral doesn't have any variable bounds anymore, then we can go ahead and just do this with the multiplication trick. So this is the same thing as 0 to pi of d theta times the integral from 0 to 3 of 3r minus r squared. Okay, well, this will give us our pi right here. And then this will give us 3/2 r squared minus r cubed over 3. That will be from 0 to 3. All right, so then what are we going to get here? We plug 3 in for here. This will be 9 times 3 is 27 over 2 minus 27 over 3. Well, if I factor out a 27 and I do a half minus a third is a sixth. So this ends up being 27 pi over 6, aka 9 pi over 2. All right, so that will be the volume of this half cone. Now, wait a minute, this is a half cone, right? We at least know a volume formula for a full cone, right? Or at least we're aware that one exists. Does anyone happen to know the volume formula for a cone, just a regular cone? Oh, yeah, what's up? That's right. So the volume of a cone is 1/3 pi r squared h. So I guess the volume of a cone that's cut in half will be 1/6 pi r squared h. Okay, well, we know this cone has a height of 3 right here. And then based on this circle, based on the circle right here, we know we have a radius 3 as well. So if I plug in r squared, which would be 9, and the height, which is 3, we end up getting 27 pi over 6, which is also 9 pi over 2. So there we go. So that was the much quicker way of doing this. And remember, at least this semester, your exam is multiple choice. So if you recognize what a shape is, and you just need to find the volume of it, if you recognize how to interpret this integral into a physical object, and you already know a good formula for that physical object, then by all means do it that way. All right. Okay, let E be the solid region bounded below by the cone Z is root x squared plus y squared, and above by the paraboloid Z is 2 minus x squared minus y squared. Find the volume of this solid. All right, let's see. So this is a cone once again. We have our cone. Now this time we're bounded above by a paraboloid. So this paraboloid starts at a height of 2, and then as we go outwards, remember this is 2 minus r squared right here. It's going to end up kind of descending down like this. So we kind of have this kind of blob, this circular blob on top of the cone. So this kind of looks like an ice cream cone. So here's where my funny story comes in. So I've actually seen this problem before back when I tutored Calc 3 in undergrad here, or not, no, sorry, not here, at my school that I went to. So anyways, let me tell you the story. So there was a Calc 3 exam about this time in the semester, and a problem like this showed up on the Calc 3 exam right here. So this showed up on the exam. So after the exam, people were talking about this. Anyways, in a seemingly unrelated note, I was actually going on a date to this restaurant in the city. It was Pittsburgh. And so me and my date sit down in the restaurant, and it was at one of those restaurants where all the tables are like so close together that you can hear other people's conversations. So like you're kind of like within their sphere of conversing. So anyways, me and my date were like some of the first people in this restaurant. So we're just talking to each other. It's going all right, I guess. And then after a little bit, these two guys sit down next to us once the restaurant starts getting filled up. So these two guys sitting at the adjacent table. And it was at this point that the girl decided to start talking about the Twilight movie, which I had admittedly a limited amount of interest in. So I started kind of listening into what these guys were saying next to me. And they were talking about this problem. They were talking about this ice cream cone problem. And one of them said like, oh yeah, well, you could do it by just finding the volume of the cone down here. And then the top is obviously going to be a sphere. And the volume of a sphere is 4 pi r. So you're just able to do it that way. And I was listening to this, and it was obviously wrong. Not even just the volume of the sphere formula, but like this isn't a sphere. And so like I just couldn't resist. So like, oh, I was like, oh, excuse me, I'm sorry to interrupt, but the volume of a sphere is actually 4/3 pi r cubed. And so I talked to them for a minute on like how to actually do this problem. And they weren't mad or anything. Like they appreciated I did it. Who was kind of disappointed was the girl I was with, and about 5 minutes later, she had a personal emergency to attend to. So she decided to go home after that. So anyways, so I'll never forget how to do this problem because it cost me, well, it was honestly me that cost me the day by talking to other people, but you know what I'm saying. It's a memorable thing. All right, anyways, let's actually figure out how to do this problem for real. So what we're going to do is we're going to set this up in terms of cylindrical coordinates. All right, so with cylindrical coordinates, we have an r in there for sure. And we're just doing a volume. So we're just integrating 1 besides that. All right, so my lower bound for this is going to be the cone, right? My lower bound is the cone, and we just saw in the previous problem how to write that in terms of cylindrical coordinates. It's just going to be z is the square root of r squared, or r. And then the upper bound is not a sphere, it's the paraboloid. It's 2 minus r squared in terms of cylindrical coordinates. All right, now they didn't put any restrictions on this being in the first quadrant or anything like that. What will our theta bounds at least be? Theta will go all the way around from 0 to 2 pi. But what's the equation of the circle where they end up meeting at? Well, what we need to do is we need to set z as 2 minus r squared equal to z equals r, and we need to see where these guys intersect. So we have r is 2 minus r squared right here. So we added r squared and then subtract 2. And then we can factor this here. We have r plus 2 r minus 1 is 0. Now this gives us two options. We can have r is 1 or r is -2. And why does r equals -2 make sense? Well, if we were willing to have negative r values and hence negative z values, this cone would turn into an hourglass. And the paraboloid would also meet the cone going down this way at r is -2. But since we're forbidding negative r's from occurring, this must happen at r equals 1. And the equation r equals 1 is, of course, the unit circle right here. Why is r below 2 minus r squared? Because we're bounded below, or sorry, bounded above. So we're bounded above by this, meaning that our shape is below that. So we have z is 2 minus r squared. Would it work to make the bounds of z from 0 to 2 and then make the function in the integral of top minus bottom? Yeah, so that's effectively what's going to end up happening here. Although the z bounds wouldn't be from 0 to 2. We just wouldn't have z anymore. We would do this minus this and then just have a double integral with dr d theta. That's another way of doing this problem right here. All right, but anyways, we know our r goes from 0 to 1 now. All right, so let's go ahead and do this. So I integrate r with respect to z, and I get rz. Okay, and then I plug z, or these in for z right here. All righty, and then this, I think it was Lauren that was talking about this. This is what, I'm assuming this is what you meant. So we could do the top surface minus the bottom surface times r, and then have dr d theta with polar coordinates. That's an equivalent way of doing this problem. All right, so let's go ahead and distribute this out. Oh, everything is constant bound now, so I could just have d theta here. So we have 2r minus r cubed minus r squared from 0 to 1. All right, so let's go ahead and do this. This is going to be 2 pi. And then the integral of this will be r squared minus r to the 4th over 4 minus r cubed over 3. Okay, so I have, if I plug 1 and 0 in here, I have 2 pi, and then I have 1 minus a 4th minus a 3rd. Let's see, I think this fraction in here will be 5/12. So we end up with 5 pi over 6 as our volume right here. That's how we actually do this problem. Unfortunately, we can't just do a half sphere volume over a cone volume. It's a little bit more involved. All right, let's do one more and then you guys can have a good weekend here. So find the volume of the solid that lies inside the cylinder, x squared plus y squared minus 2x is 0, and under the sphere, x squared plus y squared plus z squared is 4, and this will be in the first octet right here. All right, so what I'm going to do here to see where this cylinder is centered, I'm going to complete the square here. So I have x squared plus y, or I'm going to group the x squared next to the negative 2x. So I have x squared minus 2x plus y squared. So my magic number that I'm going to add to both sides here to complete the square is 1. So I have x squared minus 2x plus 1 plus y squared is 1. And then this will turn into x minus 1 squared plus y squared is 1. All right, so in the xy plane, this describes a circle of radius 1 that's centered at the point 1, 0. So I'll be right here. This is our cylinder from the top down. If I draw it here. We're in the first octet. So forget about this. All right, so we're in the first octet, and then we have our sphere kind of above that right here. kind of like this. All right, so this is going to be our thing that we're integrating over. So the cylinder pretty much just made our domain right here. And the thing that we're integrating under is the sphere equation. So let's go ahead and solve the sphere equation for z, because we're going to need to have z bounds for our cylindrical integral. So we're doing a volume, so it's just r dz dr d theta right here. All right, so I'm going to subtract y squared and x squared. So I have z squared is 4 minus x squared minus y squared. So z squared is 4 minus r squared, meaning that z is the square root of 4 minus r squared. All right, so this is going to be my upper bound because my upper bound is bound by the sphere here. And then my lower bound, what's my lower bound going to be? Does anyone know what the lower bound is? Got some zeros here. And that's actually right. 0, because we're bound by the first octave. So when we go down here, we're bounded below in the z direction by that right there. So it's 0 to root 4 minus r squared. All right, now we need to do our r bounds. Now our r bounds won't be as easy as they usually are. So we have r equals 0 because we include the origin. So that much is for sure. But this time our circle is not centered at the origin. Our circle is centered at the point 1, 0. It has a radius 1. But more importantly, it has a diameter of 2. You guys remember how to find the equation of a circle of diameter 2 in the x direction? Yeah, it looks like some people in the chat remember it. It's going to be 2 cosine of theta. So this curve right here is ours 2 cosine theta. So this is a thing definitely worth remembering. If you have a circle that just barely touches the origin and has diameter, I guess in general, a, in the x direction, the equation will be r is a cosine theta. And as you could probably guess, if we want one in the y direction, it'll be r is a sine of theta right here. All right, so now we need to do the theta bounds for this. So let's figure out which thetas are going to get us this half circle here. So theta equals 0. If I plug that into this, I get 2. So that means I'm coming out here. Then as I rotate through my thetas, I get closer and closer until I get back to the origin at theta equals what? That's right, guys. It's going to be pi over 2. So 0 to pi over 2. Now, I saw someone earlier say negative pi over 2 to pi over 2. That would be if we wanted the whole circle right here. So if we didn't have this first octet limitation, or at least y could be negative, then it would be negative pi over 2 to pi over 2. All right, this one we're not going to be able to use the multiplication trick at all because we have a variable bound every step of the way. So this one we're going to have to do an iterated integral here. All right. So let's see here. Let's do the integral of r with respect to z, but that will just be, oops. That will just be r times z from 0 to root 4 minus r squared. Okay, so then we have 0 to pi over 2, 0 to 2 cosine of theta, and then we have r root 4 minus r squared. We'll put 0 in there. And then we have r root 4 minus r squared dr d theta here. All right, let's see here. So now we need to do this integral with respect to r. And I guess once again, trig sub is an option here, but I'm just going to go ahead and use u sub for this. So my u will be 4 minus r squared. Du will be negative 2r dr. And then I'm going to divide by negative 2 here. All right. So now what's my integral going to be? It's going to be negative 1/2 the square root of u du d theta. All right, so the integral of the square root of something is going to be that to the 3/2 times 1/3, which is 2/3. So when all is said and done, when we do this power rule, we're going to have -1/3 u to the 3/2 from r is 0 to r is 2 cosine theta. Now substituting this back, because I didn't want to have to change this into u's. That would be really ugly. We'd have -1/3 4 minus r squared to the 3/2. All right. So let's go ahead and plug these in. -1/3, we have 4 minus 4 cosine squared of theta to the 3/2. And then we subtract when we plug in 2 here. But that's really going to be adding 4 to the 3/2 over 3. Okay. And Dr. Huang put extra paper for like some of the ones where we didn't need it, and then we do need it on this one, and then we don't have it. So I'm just going to flip this upside down here. Actually, do we have time to finish this? Oh, wow. Yeah, we have a lot of time. All right, good. Okay, so let's go ahead and finish this integral here. First of all, I could factor out 4 to the 3/2 and I guess 1/3 out of everything. So 4 to the 3/2 is 8. So this is 8/3. And then what do we have left over? It's going to be 1 minus 4, or sorry, we pulled the 4 out of that. So it's 1 minus cosine squared of theta to the 3/2 here. So what I did was I pulled out 8/3 from everything. And I got a 4 out of here, and 4 to 3/2 is 8. And then this was also a 4 to 3/2, which is 8. Okay. So let's see here. We have 1 minus cosine squared. Well, we all know what that is. It's sine squared. To the 3/2. All right, well, sine squared of the 3/2 will be sine cubed. Okay, so we've reduced this problem to just computing what the integral of sine cubed is. Now that is a Calc 2 integral. Does anyone remember how we do integral of sine cubed, or integral of an odd power of sine or cosine? There we go. Yeah, Michael's got the right idea. Yeah, we split off a sine squared, or a sine equivalently, and we change the sine squared into 1 minus cosine squared. That's absolutely right. But before we do that, I'm just going to integrate 1 with respect to theta and get theta. And then if I plug these bounds in, it's going to be pi over 2. So I end up with 4 pi over 3 when I do that, minus 8/3, the integral of sine squared of theta times sine of theta d theta, which now I will take your suggestion and turn that into cosine squared. Yeah, use an integral calculator. Yeah, that might be a good idea at this point. This one's taking a long time. All right, so let's do u is cosine of theta, and du will be negative sine of theta d theta. So this will be 4 pi over 3 plus 8/3 times the integral of 1 minus u squared du. And then the bounds will be from 1 to 0. And why will the bounds be 1 to 0 here? Well, if I plug in my lower bound, I have cosine of 0 is 1. If I plug in my upper bound, I have cosine of pi over 2 is 0. So I get this. So this is the same thing if I want to flip the bounds in the correct order of u squared minus 1 du. All right, so we're finally able to do this. We're finally downgraded this to a Calc 1 integral. So this is u cubed over 3 minus u from 0 to 1. Let's see, I plug in 1 here. I have 1/3 minus 1 is negative 2/3. So I have 4 pi over 3 minus 16 over 9, because this was negative 2/3. All right, and there we go. There's the volume of our, what was it again? It's been so long. Oh yeah, it was the volume under a sphere that's above this cylinder right here. So but hopefully the main point of this problem wasn't doing all this, although I guess it was a good Calc 2 refresher. The main point of the problem was setting up this right here. That's really what I want you guys to take away from this is how to set up an integral in cylindrical coordinates here. Because I know that given enough time or dedication or integral calculators, you guys will be able to do the rest of this here. All right. Wow, looks like we got done a few minutes early despite that extra long integral. So I will see you guys on Monday, where we'll do this all over again, only for spherical coordinates instead.